Thanks, Chris. Great information. So hello, my name is Phil Lenk. For those who don't know me, I'm currently a product manager at Micro-Coax. Been there since 2011 in various positions, both in inside operations, inside engineering, external engineering, and sales field work. And I'm going to walk you through a little bit of our coaxial cable portion that we at Micro-Coax focus on there. And through these talks, I'm going to try to make a little reference and analogies to the music world, because if we take a step back, audio and music is RF that we can hear, and how can we use that to simulate and understand microwaves that we can't see and we can hear? Yeah, so let's start unpacking this, and starting with really the coaxial cable in its basis. So thinking of things that were innovated, at Micro-Coax, we take pride in innovating the semi-rigid coaxial cable. Nearly 100 years ago, our founder owned the patent to metal shielded wire. And that's what's shown on the left here is a very simple RF cable, center conductor, dielectric outer conductor. That's great. It has fantastic properties. It's very smooth conductor. It's great at transmitting energy down it, but it's rigid, it's stiff, and there still has many applications today. But it's been around the block a few times, and we're looking to say, how can we take that to the next level? How do we take that simple RF cable and make it where I can flex it and put it into whatever the heck I wanted to put it into? And that's the second picture here. We take that outer conductor, which is a rigid copper tube or aluminum or a different material, and add more flexible type metal layers that can now move around a little bit. And now we have a flexible cable. That's wonderful. And then how do we take it a step further? That's the picture on the right, which is that same basic cable on the first few layers. And then the bottom half of that shows these more ruggedization and armor type layers, be that internal or external armoring. And through that, we're seeing how can we minimize the loss that's introduced into the cable? How do we reduce the reflections that are happening inside of the cable? And I'll go through a couple examples with that, but there's a lot of know-how and design that go into making a cable that can do those things and transmit your signal properly through it. And not just the cable, but on the far right, we have the connectors. Connectors also have to be designed and maintained and installed in manners that will minimize mismatches, impedance mismatches, or reflection that VisWire gets introduced into the system. So here is a simple case study looking at two typical cables in the industry and looking how they perform over an S2 line or an insertion loss plot. So taking the step back to audio world, things that we can hear, imagine you're playing guitar and you have a nice long run from here to the back of the room where my amplifier is at, but I chose a really poor quality cable that introduced distortion and noise. When I'm playing guitar, I love distortion, but when I'm trying to give an RF signal, I don't like distortion. So I need to pick a cable that's of high quality that can really transmit that signal properly. So here, looking at the black line, we have a industry standard 190 cable. That's 190 thousandths diameter at the OD. That's rated up to 26.5 gigahertz, very common. And at Micro-Coax, we took a kind of different philosophy where we started with a conductor that was inherently larger in order to give us a better insertion loss signal across the length of that cable, while still maintaining that 26.5 gigahertz line size, which then pushed the diameter a little bit bigger, but we have ways of mitigating some of those different properties there. So within that, we're able to maintain geometry and signal integrity to minimize signal loss within your system. And as Chris was going through those examples of our fictitious system, we need to have ways to mitigate loss and noise and distortion throughout it there. So speaking of loss, noise, and distortion, let's talk about noise for a couple of things here. So noise, which we heard a few times come into this room now, is unwanted signals that are getting into our transmission path. And within a cable assembly, one of those points that we showed in our system, there were a number of cases which can lead to that. So back to the audio analogy, imagine who's a popular singer to these days? Taylor Swift. She's recording a new acoustic track, just her and a guitar in a sound booth, and it's going to be very lovely, nice and rich sound coming through, but for some reason in the recording studio next door to her is Slipknot or Dream Theater. Somebody's playing very, very heavy music, but the walls were not engineered properly to mitigate that sound propagation into her. So now she's getting all this external sound into her sound booth, and we're getting this noise, unwanted noise, and it's a similar concept within our cables. Like that audio engineer should have designed a better wall or a better insulation in that wall, but they didn't for some reason. We take that same philosophy, not audio, but of RF microwave energy within our cables, cable designs, and connectors. So thinking of RF ingress, some of those things that we need to care about is crosstalks. In the picture on the right, we have a high density parallel runs of cable where signals, if they're not properly shielded, could go from one to the other, or even external influences coming into that outside of there. Within the connector design, how are those internal designs maintained for the connections to happen? How are the joints? Are they attached to the cable with a crimp or with a solder? At Micro-Coax, we exclusively use solder connections to give a nice full solder around the back of the connector to the cable. Again, to have a nice solid thing with no voids. If you have some crimps, sometimes there could be pinholes in allowing energy to come in or energy to go out. All things to consider there within the cable itself and cable shielding. How is that used to mitigate unwanted noise? So let's look at two case studies. On the left, the very first picture you'll see is a typical two-shielded coaxial cable, not unlike the ones we saw earlier that can be rated up to 26.5 gigahertz, very common. And on the bottom left graph, you see a dotted dashed line. That was tested and measured at our factory where we have a stirred mode reverberation chamber to test RF shielding properties. And that cable performed out to 18 gigahertz, roughly around 65 dB of loss through the cable. And one of the things that we developed at Micro-Coax is a product called Aerocon. And if you look at my socks today, I'm actually wearing Aerocon socks. And to lighten it up a little bit, if each of you just takes one moment and reaches underneath your seats, yeah, you'll find there's nothing there. But in the back, we do have socks for you to pick up on your way out if you haven't get one. But Aerocon it's not actually a cotton, it's a Kevlar-based fiber, a textile that we then metallized and plate in-house at Micro-Coax. And in this example, we took this shield, put it over top of that same wire, tested it in the same manner, in the same chamber, and that gave a 30 dB of improvement of shielding. So basically riding the noise filler of our chambers. So this is a fantastic material, which is, if you can kind of think of an analogy of a chainmail suit, which you would wear in typical combat and armoring, it has a lot of holes, but you can still move it around versus my t-shirt here, which is very dense fibers, and that's more like our Aerocon, so it's fantastic at rejecting high frequency energy into our cables. And the other picture on the right is for an industry standard SMP, typically out to 18 gigahertz, which we measured on the bottom right graph there. We see typical shielding, that's either noise coming in, noise going out through that push-on interface at 65 dB. Now at Micro-Coax, we developed a new technique on our female connectors that was able to push that up another 15 dB, which pushes a standard SMP interface up to 80 dB, which is pretty industry changing, and we're very proud of that recent design. Still completely intermatable with other third-party connectors or our own male connectors. I'm happy to talk more about that. So lastly, we're going to end with sources of distortion within our cable. Again, we heard distortion today multiple times. And back to the audio analogy, if I'm playing guitar, I want to have distortion in my signal. Typically, if I'm playing something heavier or reverb or chorus. But if I'm making VNA test leads, the last thing I want to have is that distortion introduced into the cable, especially after a fresh calibration and you're going to do a whole day of testing. This past year, we had a lot of hard work go into our latest AccuPhase test cables, which are meant to be calibrated once in the beginning of the day, be flexed, moved, banged around, moved, tested all day long, and still hold that initial change, especially in regards to phase versus flexing, particularly in these models here, where they're meant to mitigate any of those distortion introduced through bending, movement, vibrations. And it didn't come overnight. It came over those decades of experience that we built into our Utaflex products and know-how within the industry of the metals and various techniques of cable and cable building. So with that, I wrap it up here, and say that, when we're looking at a system, it's not just one part, but the whole system must be evaluated and work together to provide, an ultimate wave to go through. So with that, I stop and I hand it over to Evan. Good luck.